This is 1973, number 45. And let's look at what we have. Key thing, we have a continuous function on a closed interval. We don't have differentiability. So think about this, are based on theorems that you've gone over. If you have a continuous function, you have the intermediate value theorem that's guaranteed, but you don't have mean value theorem or Rolle's theorem. So let's look at some stuff here. Does the derivative always exist if a function's continuous? And the answer is going to be no, because if there's a sharp point, the derivative won't always exist. So you're not guaranteed that the derivative exists everywhere. So it's an important thing that you've seen. If the derivative exists, you know a function's continuous everywhere, but not the backwards of that, not the converse. Okay. If you have a maximum value, does it have to have the derivative be 0 at that point? And the answer is no, because maximums occur at critical points or endpoints. And a critical point doesn't have to be a derivative of 0, it could be undefined. So just because you have a maximum doesn't mean the derivative is 0. It might be, but it could be a derivative non-existent, or it could be an endpoint. So that doesn't have to be true. I'm going to skip C and come back to that. Let me look at D. Does the derivative have to equal 0? I'm going to say no. I'm going to give you some examples. Here's a continuous function. Does the derivative equal 0 anywhere on that line? No. The only way you're guaranteed the derivative is 0 is Rolle's theorem. Rolle's theorem says if you have a continuous function and differentiable, if the endpoints have the same y value, there must be at least one point where the derivative will have a slope of 0. But that's only if the endpoints have the same y value and it's differentiable inside and it's continuous. You don't have all those, so Rolle's theorem won't apply, so therefore you're not guaranteed the derivative being 0. Okay? The graph of f prime is a straight line. That makes no sense. They're saying f prime is just a straight line. It could be anything. I mean, that's obviously wrong, right? The derivative doesn't have to be x or 3x or 5x or 5x plus 3. The derivative of a continuous function you've seen could be sine, cosine, could be a lot of things. So clearly that's not true. By process of elimination, we choose C and we're done. No, we're not done. Why C? This was in chapter 2. You had a theorem on the limit of a composition of functions, okay? You actually had a theorem that says if you have this f of g of x and you want to take the limit as x approaches x naught, the theorem said it actually equals f, and you take the limit of the inside function. Do you remember that theorem? This theorem was true if your function's continuous. I don't know if you probably remember that theorem vaguely, but if you have a function in a function and you want the limit, you could take the limit of the inside, then plug it into f. I'll give you an example of that just to help you remember. What if you had the square root of x minus 2 and you want the limit as x approaches 3? Well, that's a function of function. You could take the limit of the inside and then plug it into the square root. Basically, that's what's happening. So the limit of the inside would be 1, and the square root of that inside limit is your answer. So that's basically what this is saying, but in an even more simplified form. Okay? So that is number 45.